welcome to the 24th episode of the Silicon Valley Quantum Computing Group. I am your presenter, Taposh Roy. I'm a host, actually. I have with me Dr. Manjula Gandhi, who is going to be our presenter and who's going to walk us through the building reversible circuits with quantum gates. It's going to be a hands-on session and it will be multiple sessions. So this is the first of multiple to come. About me, I'm the Director of Innovation and AI at Kaiser Permanente. My focus is on digital twins, responsible AI, and even quantum in that sense. I am at Harvard Medical School, where my research area is in the intersection of multiple domains, which is quantum, AI, as well as medicine, and how this impacts human health, life, and decision making. Before we go there, I wanted to just take a brief moment and talk about the phenomenal times we are in. I'm first going to talk about uh, April 14th, which is celebrated as the World Quantum Day. This is the day where Planck's constant resonates with closely with the calendar, which is 414, and that's why we celebrate that. In addition to that, last month maybe a couple of new enhancements were made. So one was MIT developing its scalable quantum interconnect processor. So it's a communication between processor to processor. It's very impressive work that's been done at MIT. This is on top of what's been done with both Majarno as well as with Google. Another initiative that DARPA in the US started is the benchmarking, and a lot of industry leaders and companies have joined that. So that's another interesting development happening. From a conferences standpoint, there are two conferences upcoming. So if there are people who want to learn, who want to participate in research or even publish their papers, there is IEEE Quantum Week that is starting on August 31st. It's in New Mexico, US. It's a multidisciplinary research an innovation conference, so industry participants are also there. And then European Union, European Quantum Technologies Conference is starting as well. But this is in Copenhagen, Denmark. With those high-level changes happening, I'm going to go to the next slide where we introduce our speaker and presenter today. Dr. Manjula Gandhi is an associate professor at Coimbatore Institute of Technology for last 24 years. She is one of the earlier person to get a IBM Qiskit advocate. This is starting from September 2020. She has her MS and PhD both in quantum computing since 2003. She has a lot of other accolades. In fact, there is a quantum gate to her name as well. I'm really honored to have such an august person in our midst and talking to us and teaching us with humility on reversing quantum circuits. I'd like to invite Dr. Gandhi to take over the presentation from here and then walk us through her materials on reversing quantum circuits and engage us in learning quantum computing. With that, Dr. Gandhi, I'm going to stop sharing and pass it on to you.
Thank you, Taposh, for inviting me and giving me an opportunity to share my experience. And I would like to thank the entire organizing team behind you and all the participants who have joined here for today's session. So my today's title will be building reversible circuits with quantum gates, and most probably we'll be having a hands-on session. Otherwise, I'll be showing the demo from my side actually. And I thank Silicon Valley Quantum Computing Group for giving me this opportunity. And my agenda for today's session, I'll be just giving an intro about the fundamentals of quantum computing, the transition from classical bits to quantum bits, and some of the quantum computing principles which we have, the various applications where we can work on with using quantum computing concepts. And mainly the circuits behind quantum systems are reversible circuits. So the difference between irreversible circuits and reversible circuits, and how to work using IBM's Qiskit composer for looking upon various single qubit quantum gates, multi-qubit quantum gates, and how we can build classical logic gates using quantum circuits, and some of my references which I have. So basically, why we are moving on to quantum computing is one thing. Our circuits in current day machines are getting miniaturized. So that is one reason we are moving. End of Moore's law is another reason why we are moving into quantum computing. The other major portion is our transistor sizes are getting shrinking. And we have a major barrier. The thing is the power dissipation, the heat which is generated from our systems, devices. And what Landrer and Feynman in 1972, what they said is, if at all, we have to dissipate the less energy, the heat has to be generated low. In that case, our circuits should be in reversible in nature. That is, we have a one-to-one mapping between our inputs and outputs, and such circuits will have zero power dissipation. And why we are talking about quantum computing for reversible circuits is all circuits in quantum computing are in reversible in nature. And my entire PhD work is we worked on constructing reversible circuits, building up applications or solving algorithms using reversible circuits. So quantum machines. They follow principles of quantum mechanics, and classical machines, we use the terms called as bits. We all know the 0 or 1, whereas quantum computers we use combinations of something called as quantum bits, where we are not just going to be in state 0 or 1 at a particular time. We can be anywhere between 0 and 1, and we can also be in both 0 and 1 at the same time actually. I had a fight with my supervisor he asked me how you can be in both the states at the same time. So that was a major issue. Earlier, when I started working from 2003, we didn't have devices, we didn't have simulators. So it was very impossible for me to show him that this is how I can be in state 0 and 1. But now we have many quantum tools available, software tools are available. I can easily show that this is what a superposition state is. Okay, so here the difference between classical machine and a quantum machine. Bits can be either be in state 0 or 1, whereas when I'm talking about a qubit, I can be in ket 0 or ket 1, and I can be in combination of zeros and ones. So ket xi is given by C1 ket 0 plus C2 ket 1, where sum of the squares of your amplitudes, that is mod C1 square plus mod C2 square, should sum up to 1. So this is the only constraint which we have for a valid quantum state. We use the principles of quantum mechanics here. We use bracket notation, and this notation we call it as ket 0 and ket 1. So sum of the squares of my amplitudes for C1 and C2 are your amplitudes. The sum of the squares should sum up to 1 is one of my condition. So this is denoted as ket 0, this is denoted as ket 1, and this is combinations of zeros and ones. That is, I'm in a superposition state. So let us consider an example of a travel agency where he is owning 2 cars and there are 3 people who are to travel using these 2 taxis. So we have a combinations of friends. A tick mark indicates that A and B are friends. A and C are indicated by cross indicates that they are enemies, and B and C are enemies. So we have a combination of taxi 0 and taxi 1 over here. So if I'm talking about 0, 0, 0 indicates that all people A, B, and C are traveling via taxi 0. If I consider this particular case, 0, 0, 1, A and B are traveling via taxi 0 and C is traveling in taxi 1. And when I'm considering the last second case, A and B are traveling via taxi 1 and C is traveling via taxi 0. So what we do, we calculate a configuration score for all of these 8 configurations, that there are 2 taxis and there are 3 people. So we have 8 different ways in which we can group them. And the configuration score, how we calculate this, friend pairs sharing the same car minus number of enemy pairs sharing the same car. So for this particular example, 001, A and B are in taxi 0, this 0, and C is traveling in taxi 1. So we don't have any enemy pairs. So we have number of friends is 1 and we have number of enemy pairs is 0. So it is 1 minus 0. Similarly, for the last second combination, when A and B are traveling using taxi 1 and C is traveling in taxi 0. So for these two configurations, we have a highest score, which is a positive score, and that is 1. And for all other configurations, we are going to have a negative. So we'll be dropping those all other 6 configurations. Now, the second scenario where we are considering is we are going to have 4 people, the same 2 taxis, and we have additional combinations of friends and enemy pairs. So here we have 16 different combinations here. So 0, 0, 0 1 indicates that A, B, and C are traveling in taxi 0 and C is traveling in taxi 1. D is traveling in taxi 1. And for calculating the configuration score, what we could do is we can write a small program for computing this particular configuration score. So number of friend pairs sharing the same car minus number of enemy pairs sharing the same car. So we have 16 different configurations and we can calculate it using a small program here. What if I'm having 100 people? So instead of taking taxis, let me take bus. So there are, we have 2 to the power 100 ways in which we can combine these buses. So that is actually, it sums up to 10 to the power 30, which is actually 1 million configurations, which is actually impossible for us to solve using a regular system. So for solving this, we'll be actually, this as just a simple example to show how I can go for computing for all values at the same time. So here, this is for 3 people, 2 taxis, that is taxi 0 and taxi 1. So we are going to have the configurations, combinations of 0, 0, 0, etc. up to 1, 1, 1. And for all of these 8, that is 2 to the power 3, which is 8 different configurations, we are going to compute on all of these 8 configurations in one operation of my quantum program. So similarly, if I move for a 4 persons, 2 to the power 4, if I'm going for 100 people, so 2 to the power 100, we'll be computing on all of those configuration values. Say, for example, if I'm talking about a 5-qubit machine, we have 2 to the power 5, which goes for 32 different values. So the computations can take place on all 32 different values in one operation of your quantum program. So if it is a single qubit machine, I can compute on both 0 and 1 at the same time. If it is a 2-qubit machine, I can compute on all of these 4 values, 0, 0, 0, 1, 1, 0, and 1, 1. And for 3-qubit machine, 2 to the power 3. For a 4-qubit machine, 2 to the power 4, and etc. So basically, quantum machines are, you're going to compute on both the universes parallelly. So we are going to compute on 0 and we're going to compute on 1 at the same time. So the number of operations which we talk via quantum, a classical machine is, we would, for the same example, we would need 10 to the power 30 operations. Whereas when I'm talking about a quantum machine, I would hardly need 1 operation. Why? Because I'm going to compute on all of my values in 1 operation of my program. But there are some drawbacks in quantum machines. The drawback is every time it will not find me the best solution. Sometimes it might find the second best solution, the third best solution, and so on. So what we are doing is, in order to solve such problems, we're going to run your program for multiple iterations. Say I'm not going to run my program for 1 shot. I'll be running it for 1024 shots. If I'm running it on real quantum devices, they are prone to errors, and we can run it for multiple number of operations in order to get the correct answers. So advantages of quantum computing is it is still much better than running the same problem on a regular computer and having it to repeat the same type of computation 1 million times. So quantum computing concepts which we have, we have concepts like superposition states. All of these made me not to leave quantum computing. My supervisor said, "Bye, Manjula, we are working on this. We'll better move to another area." He said this in 2006, but I said, "No, sir, I'm just going to continue on this." Just because of these concepts, I was not able to leave this area actually. So we have superposition states. Superposition is I'm going to exist on both the states, 0 and 1 at the same time. And we have something called as quantum entanglement, where I can sitting here, I can make another qubit behave exactly the same way as this particular qubit in the other part of the universe or on another side. We also have quantum teleportation, and quantum teleportation is we cannot make a copy of a qubit. So what we could do is we can teleport a qubit, teleport in the sense move, and quantum teleportation plays a major role in quantum key distribution and so on. Quantum algorithms, the first algorithm which came into existence was 1985, Deuce's algorithm. What Deuce showed us, you can compute on two values of a function f at one particular time. And this was the algorithm which proved that we can do huge things using quantum algorithms, quantum systems. DJ algorithm, this is Jose algorithm, which came in the year 1992. And the turning point for quantum computing field was Shor's factoring algorithm, which came in the year 1994. What Shor has proven that is you can break our RSA algorithm, cryptographic algorithm techniques. If quantum machines comes into existence, you can easily factor a very big number. So that was another huge development. And the other one was Grover's search algorithm. He showed that you can search a very big database in order of maximum of order of square root of n times. So Grover's search algorithm finds more applications in solving NP-hard problems like n-queens problem, Sudoku problem, traveling salesman problem. You can find applications of Grover's search algorithm in solving all our NP-hard problems which we're not able to solve using a classical machine. So the various next part is I'm moving on to quantum computing applications. I worked more on constructing reversible circuits. So design any circuit which you have in your classical machine, you can convert it into reversible circuits. Optimize your circuit in terms of your depth, width, and quantum gate cost, circuit cost, and so on. And there are more openings in quantum software, like IBM's Qiskit is one of the software tools. And so Classic is another quantum software which allows us a high-level programming using Classic. And we also have Circ, Penny Lane, and so on. Quantum hardware, if you are from circuit branches, I would suggest you to look into quantum hardware. There are many like openings for hardware persons. If you are good at classical machine learning, I would say look into quantum machine learning. Similarly, all the areas which we are having, image processing, we have quantum image processing, quantum compilers. If you're interested in game development of games, you can go for building quantum games. If you're interested in composing music, I would suggest James Weaver has a very good music playground dashboard there where you can go and compose your music, which is available. And finance and optimization applications are, again, we can find many applications related to those concepts. The next part is reversible circuits, so quantum circuits, which we are having. These circuits, they do not lose information. Reversible circuits can generate a unique output vector from each input and vice versa. And in reversible circuits, there is a one-to-one mapping between input and output vectors. So this is irreversible AND gate, and this is reversible AND gate. So here, if my value of A and B was 0, it is impossible for us to predict the value of A and B. That is, A can either be 0 or A can be 1, or B can be 0 or 1. So we can't say what my input was. So this is the drawback of irreversible circuits. Why? Because we are losing our inputs. And the loss of input is which is actually generated as heat in our machines. But whereas when we are talking about reversible gates, we have one-to-one mapping between our inputs and outputs, and we'll not lose our inputs, we can retain them, and we can find the output also. So how to getting started with IBM's Qiskit? You have to specify the first thing for running algorithms on quantum machines. We need the following steps. First one, decide the number of qubits and number of classical bits you're going to have in your system. Second, what sort of combination of quantum gates you're going to use such that you construct the algorithm. And these gates we apply to our qubits. And the last part is measuring. So we decide the number of qubits combination of gates, and measurement of qubits, and storing the results in classical bits. We will be actually storing our results in classical bits. So this is a sample quantum circuit. I'll just explain you what we have here. So these are qubits, Q0, Q1, Q2, Q3 indicates that they are quantum bits. So here, this is an example of a 4-qubit quantum circuit, and this double line indicates that it is classical bits. So we have 2 classical bits over here, and these are actually the quantum gates. So this is single qubit quantum gates, and if I'm operating it on 2 qubits or 3 qubits, we call them as multi-qubits. So this is operating on Q0 and Q2. Here we have Q1 and Q2, and these are quantum gates. So this is our NOT gate, which we'll be seeing in the next slide. And this is an example for CNOT gate. And this is controlled NOT gate. I'm having 2 controls and 1 NOT gate over here. And these symbols are for measurements. I'm measuring Q2 and I'm storing it in classical bit 0. And I'm measuring Q3 and I'm storing it in classical bit 1. So here we have measurement symbols, and these lines, dotted lines, are values just to show us the readability of quantum circuits. So we have our inputs here. This forms the gates, the algorithm basically. And the last part is after applying quantum gates, you're measuring some of your qubits and to obtain your results. So we'll be using quantum mechanics principle, and we use direct bracket notation for representing qubit states. So this is a state representation. So we have 3 different bases. One is Z basis, where your eigenvectors are 0 and 1. Next, we have X basis, where my eigenvectors are plus and minus. And we have Y basis, where we have I and minus I as our, I'm not moving so much into mathematical things. We are representing using vectors. So a ket 0 is represented in vector form using 1, 0. And ket 1 is represented, we read this as ket 1 and represented as 0, 1. So Z basis, your eigenstates are 0 and 1. And for Z basis, we have plus and minus. A plus state is denoted by 0 plus 1 divided by root 2. And for a minus state, we denote it by 0 minus 1 divided by root 2. And in vector form, we represent plus as 1 by root 2, 1, 1. And for minus, we represent it as 1 by root 2, 1 minus 1. And similarly for your Y, my I and minus I. So these are the other 2 representations of your ket I and ket minus I. So some of the basic quantum gates which we are having, single qubit quantum gates, we have X gate, Y gate, Z. S gate, SDG goes for S dagger, and Hadamard gate. So Hadamard gate is one which puts your qubit into a superposition state. So here, first let us start with this. So your H gate, your matrix of your H gate is 1 by root 2, 1, 1, 1 minus 1. Just with the help of these matrix, we can determine the various outputs for all my inputs. So for a particular gate, we can look into the combinations of ket 0. If my input was 0, if my input was ket 1, if my input was plus, minus, for I and minus I. For all of my 6 states, what will happen when I'm applying X gate onto it? What will happen when I'm applying Y gate onto 0? What will happen when I'm applying Hadamard gate onto 0? So that is what we'll be actually showing in the demo here. So, and this is for your Z gate. Z gate is, again, we have the matrix representation of Z gate is 1, 0, 0, minus 1. And for S, we have 1, 0, and 0. We also have S T gate, and we have rotation gates Rx, Ry, and Rz. So there are many quantum gates which help us. And we can move from one state to another state. Say, for example, I want my I. So what I can do is I can get my I starting from 0. I'll apply my Hadamard gate. It will take me to plus. And if I apply my S, it will take me to I. Okay. So we'll see this in the demonstration purpose sign. So I'll be showing the demo of working with single qubit quantum gates using IBM Qiskit Compose. So how to create for the first time users, if you're here for the first time, what I would ask you guys to do is go for quantum.ibm.com quantum.ibm.com, and here create an ID. You'll have, for the first time users, you can create an IBM ID here. So I'm just logging in via my ID. I'm logging into via my ID and to work on with various quantum bits, the gates which we have. So we'll see how to work using quantum bits. Here on the bottom, you will have IBM Quantum Composer here. So just go with this, go with a file, new file here. I'll just explain you what these dashboard contains. So here you have the various quantum gates which are available. So we have the NOT gate, H gate, I gate, T, S, Z, R, Z, P, so many other gates which we have here. And this notation is for measurement, and this is for reset. And these are multi-qubit quantum gates which are available for us. And using them, we can do so much operations here. And this is auto-generated code. So whatever changes we make here in the gate connections, here the code will be auto-generated. Or if you want, I can also redo here. Say, for example, I want only one classical bit. I can do this here. I can also reduce it here. I just want one single qubit. So you could see the dashboard. Now we have a single qubit and we have one classical bit in this example. So the first quantum gate which we'll be using here is, I'm just starting off with my NOT gate. And look at the bottom of my screen, you have the various output representations. So we have here the probabilities and the Q-sphere output representation, and we also have state vector representation over here. So initially, I'm having zero. Let me start with reset option here. So 0. And let us show the inspect over here. So I'm inspecting it. I'm starting from 0. So look at this. This is your 0 state. So in your Q sphere, this is represented by top upward line is shown by 0. I can also show you here in my state vector representation. So get 0 is represented by, and Qiskit is upon Python. So it uses complex number notation here. So 1 plus 0 j. And 0 plus 0j for get 0. And then we are applying X gate. Your X gate is classical NOT gate. So look at the probabilities. 1 is now 100%. And your Q sphere, your 0 is now moved on to state 1. And look at this. Your output is now, this is for get state 1. So we have 0 plus 0j and 1 plus 0j over here. Let me stop inspecting here. Let me add one more qubit. So add 1. You can add qubits here. So we just move on. Now if I want for 2 qubits, so what is my combination we are having? So let me show for delete this. Add a Hadamard gate here. So I'm starting with 0. Let me inspect here. Again, I'll just do one thing. I'll just delete this for the argument. I'm starting with get 0 here, so 0. And then I'm applying Hadamard gate onto my get 0. So onto my 0, if I'm applying my Hadamard gate, now I'm in 50% 0 and 50% 1. So this is what I meant by I can compute on both the values 0 and 1 at the same time. So here you have 0 and 1, and you get your state vector representation of your place state. Okay, which is 1 by root 2 0 and 1 by root 2 1. 1 by root 2's value is 0.707, and we don't have any phase value, so plus 0j. Again, for the other one, so for get 1, 0.707 plus 0j. Let us stop this. Let me have for the minus state. So I'm applying. So again, let me inspect. So I'm starting here. So we started from get 0. We are starting from get 0. So 0, 100% probability, and your output state is 1 plus 0j, comma 0 plus 0j. Next is we have plus state 0 plus 0j, comma 1 plus 0j over here. And then Hadamard. So this is now my minus state. So we have 0 minus 1 divided by root 2. So look at the phase change value here. So we have this is for 0 and this is for minus 1. So get 0, 1 by root 2 get 0, minus 1 by root 2 get 1. So we have these values. And you could see whatever changes you're doing it here are dynamically updated in your CASM columns. Next is, let us just deleting this. I can also show you. This is your state I. So on 0, I apply Hadamard gate, and then on plus, I'll apply S. So inspect that. So we start from 0. This is your get 0. Next is moving on to Hadamard, 50% 0 and 50% 1. And then you go for your state is. So this is your state is 0.707 plus 0j, comma 0 plus 0.707g. So this is my state I. So next portion is multi-qubit quantum gates. So we have multi-qubit states. So where we have say, for example, this is a 2-qubit gate. In that sense, we have 4 possible states, 0, 0, 0, 1, 1, 0, and 1, 1. So we have a random state. Get A is denoted by A0, 0 plus 0, 0. Get 0, 0 plus A0, 1, get 0, 1 plus A1, 0, get 1, 0 plus A1, 1, get 1, 1. And where we have the sum of the squares of my amplitudes, that is mod A0 square plus A01 square plus A10 square plus mod of A11 square should sum up to 1 for a valid quantum state. So I can have this to be 0.25, 0.25, 0.25. So equal probabilities, or I can have any combinations, but only thing, my sum of my squares of my amplitudes should sum up to 1. So we have various multi-qubit quantum gates which are there, which we have. So we have CNOT gate. How this gate operates is, if my control qubit is 1, my target qubit will get flipped. I'll show you this using the demo. A very important quantum gate which is used for various applications. One is quantum entanglement, quantum teleportation. All will be using CNOT gate, which is also called as Feynman gate. Multi-qubit gate, we also have CZ gate. I'll show you the demonstration of all these. So CZ, how the difference between CX and CZ is, if your control qubit is 1, you apply X gate onto your target qubit if it is in CX. And for CZ, if the control qubit is 1, you will apply Z gate onto your target qubit. Otherwise, you remain, you don't do anything. And we have swap gate. We can swap the values of 2 qubits. We also have control swap gate. And this was a gate which we used for CC-NOT gate. Controlled NOT. I'll show you the demo of all of these concepts. So let me add one more qubit here. If I want, I can add one more classical bit. I'm just deleting all of these. So I'm starting both of them in gate 0. So one thing which I want to show is equal superposition of all states, all combinations. So if it is a 2-qubit mission, I can compute on 0, 0, 0, 1, 1, 0, and 1, 1 on all 4 values. So if I want this to be a 3-qubit mission, I can add one more qubit. And I can show you, I can start in gate 0 here. And I can put all states in equal superposition states. So this was our example of 2 taxis and 3 people, taxi 0 and taxi 1. So this is the combination of both A and B are traveling in taxi 0. and C is traveling in taxi 1 for 0, 0, 1. And similarly for 1, 1, 0, I can have A and B are traveling in taxi 1 and C is traveling in taxi 0. So we have equal probabilities of all of the states. On all configurations we can compute, and the solution is the one which we have, the one which we have the highest amplitude will be our solution. So this is what we can do for our travel agency person. So I'm just removing these Hadamard gates here. Let me remove Q2 also. Q2, I want Q2, I want Q3. So I'm having 2 qubits now. So let me work out with CNOT gate. So CNOT gate, what does it do? So I'm here in two states, so these 2 qubits alone. So 0, 0, 0, 1, 1, 0, and 1, 1. And initially we started from, let us inspect this. Initially we are starting, both my qubits are in 0, 0 state. And next is we are applying CNOT gate to it. So if I'm applying CNOT, if my control qubit is 0, my target qubit will remain unaltered. So we are going to be in the same state 0, 0 itself. So let us do one thing here. Let me make my control qubit to be 1 over here. So I have 0, I have 1, and this is 0. So let us inspect this particular quantum circuit. Move to the other part. So my state vector output representation will help you. So we have, let us start 0, 0 here. So we are in state 0, 0. And then we are applying 1. And remember, this version of Qiskit uses little endian notation. So your 1 is onto your left. Sorry, 1 is onto your right end. Right. So this is Q0. This 1 is Q0. And next 0 is my Q1. Okay. So since my control qubit is 1, my target qubit will get flipped. So if this is 1, this 0 will be flipped off to 1. Okay, so we'll have my output to be 1, 1 in this case. So we initially started with 0, 0, and we are now moved on to state 1, 1. So look at your state vector representation. So 1, 1, the highest one is, we don't have for 0, 0, 0, 1, 1, 0, we have the values as 0 plus 0j, whereas for 1, 1, we'll have 1 plus 0j. So a very important quantum gate which helps us in many applications where we can use this. I can also do another one. Let me add a NOT gate here. So initially we are starting from 0, 0. So both are in 0, 0. And then we move to 1, 1. So this is 1, 1. And now if my control qubit is 1, my target qubit will get flipped. So your control qubit remains unaltered and your target qubit now it just gets flipped. So 1, 0 over here. So a very important quantity. Similarly, I can go for CZ. I can delete CX. I can go for CZ. So add a Z over here and then I can add a 100. I can add a control here. So let me have Q0 as my control and my target is the second here. So I can add. And now what happens? So let us inspect this. So we start from 0, 0. Next is we have changed to 1, 1. And now if my top qubit is 1, my bottom qubit now it changes to minus 1, 1. So we have my phase change here. So we have your state vector output as minus 1 plus 0j. Minus 1 plus 0j for state 1, 1. And for all others, we don't have any. So this is how your CZ gate works. The next qubit which we had was another qubit. Let me add another qubit here. So let us go for control to control X. So this was the circuit which I used in reversible AND gate. So reversible AND gate, if both my control qubits are 1, my third qubit will get flipped. So third qubit, let me take that also is 0 here. So initially, let us inspect this. I'm starting from 0, 0, 0, and then I'm moving on. So we have 1, 1, 0. That is 1, 1. Q0 is 1, Q1 is 1, and Q2 is 0. So we read it as from your right end to 1, 1, 0. And now If both my control qubits, that is, if both these two qubits are 1, my third qubit will get flipped. So 1, 1, we'll have zeros changed to 1 by because it is getting flipped. So we have 1, 1, 1. So look at the dynamic auto generation of your CASM code, which is generated. Majority of questions, if at all, if you're taking up certification exam, Qiskit certification exam, maximum at least 70% of questions are from composite portion. They'll ask you lines like they can give you a sample code and they can ask you arrange this as part of your CASM. So which will come first? Say for example, your head of file, what includes you're doing, how then comes your registers, and then comes your whatever code you have given. So the rearrangement of this, and they can give you a sample circuit here, and they can ask you what will be your Q-sphere output. They can ask you what can be your state vector output, and so on. Predict your outputs. They can give you your state vector, and they can ask you to choose the correct circuit diagram for getting those circuits. So these way are majority of our questions. So I would say probably 70% of questions are from basic fundamental quantum gates. So by this, we actually set out for classical, logical, or logical NOT, and so on. I can also show you a demo of, let me go to my PPT. So this is how you work with multiple quantum gates. So till now, what we have seen is difference between classical bits and quantum bits, irreversible circuits and reversible circuits, how you can transit from irreversible circuits to reversible circuits, creating quantum circuits using IBM Qiskit, visualizations like state vector visualization and Q-sphere visualization. There is another visualization called as block sphere. Difference between a block sphere and a Q-sphere is two-dimensional representation, whereas a block sphere is a three-dimensional view. And Q-sphere will show us the phase change, whereas block sphere will not show phase changes. And Q-sphere, if I'm talking about multiple qubits, I can show the values of multiple qubits in one Q-sphere. Whereas when I'm talking about a block sphere, we have block sphere for each qubit separately. Say for Q0, you have one block sphere. For Q1, I'll have another block sphere, and so on. So this was my interview question. I had an interview question where they asked me, what is the difference between Q-sphere and block sphere, and what do you prefer? Which one you like? So that was my question over there. And the next part was we saw some of the quantum single qubit quantum gates like X gate, H Hadamard gate, S gate, T gate, and so on. And multiple qubit gates, we saw some like CX, CZ, swap gates. And 3-qubit gates, we saw controlled X, which forms a major portion in your classical logic gate building. So if you are interested, what you could do is you can go for building up classical logic gates using quantum gates. Say, for example, I'm just going to apply a NOT gate to my single qubit quantum gate. It becomes my classical NOT. If I want AND gate, I can go for the one which I showed you using CCX, controlled X will take you, and you can apply, you can find for classical AND gate. NAND gate, apply NOT to your AND, or the demonstration circuit which I used you to show for very simple, the first circuit which I showed you as one of the quantum IBM Qiskit circuit I was talking about, that is for classical R. Okay, this circuit is for classical R. You apply a NOT at the end, it becomes NOR gate. Okay, so these will actually work, and you can build up using all basic quantum gates. You can build up your classical circuits. So I also have a code for implementing classical logic gates using the various quantum gates, and I'm executing it here using simulator here. So this is for NOT gate. Local installation of Qiskit upon Jupyter Notebook you have installed, and you can install Qiskit and then work on it. Or either you can also, if you're interested, you can also go for a lab and work using on your notebooks. This is for my NOT gate. And the symbols here we have, this is for my measure, this is for draw, for executing it on a backend, on a simulator, the number of shots, runs, and a function. running it in a background for how many shots, and getting out my results. This is for your NOT gate. This is for AND gate. So your circuit for your AND is control NOT. If you're not interested in local installation of Qiskit, I would say you can work using composer itself. Try for various combinations. For 0, 0, what your output is going to be. So the truth table for AND gate, if it is 0, 0, my output is going to be 0. If it is 0, 1, my output is going to be 0. If it is 1, 0, my output is going to be 0. And if it is 1, 1, my output is going to be 1. Okay, so similarly, you can work for all other logic gates. This is for all various combinations. This is for NAND. So we apply a NOT gate after applying CCX, that is for AND. And this is for OR gate. So OR gate, a most interesting one. So this is XOR. XOR CX gate works exactly like your XOR. So 0, 0, 0, 1, 1, 0, 1, 1, my output is going to be. So for 0, 0, we don't have any change. For 0, 1, will not have any change. For 1, 0, my output will be 1, 1. And for 1, 1, your output will be 1, 0. And this is for your OR gate. Okay. So just note out these quantum gates, and you can use them using your composer, and you can find and you can do various inputs, your combinations of 0, 0, 0, 1, 1, 0, and 1, 1, and you can find it.
Dr. Gandhi,
So,
should we pause to see if there are any questions? It's 9:47
yes.
here.
Yeah,
I know there
Taposh,
is
your
no.
volume is little low for me.
Oh,
Can I have an?
can you guys can you hear me? Okay. Yeah. Do you want to pause a bit for questions so we give some chance to the audience, and also there will be a follow-up session. You covered a lot of ground today for people who are new. It might take them some time. Um,
Yeah.
so let's see if there are some questions from the audience. You can either put it on the chat or you can unmute and ask as well.
Hello everyone, I'm Abhinav. I have a few questions and these are more about fundamentals. So let's say there is a n qubit system, right? And we are doing a matrix multiplication. Is the complexity of operation order 1 or considered order n?
We're talking about matrix multiplication here.
Yes. Let's say we are applying CNOT on a 2 qubit system. So I'm trying to understand where is the power coming from. So the matrix will be considered a unit operation, is it? Or it is still order n?
Not getting a question actually. If I'm talking about CX gate, I'm just going for matrix multiplication. We are not talking about the the cost matrix depending upon your multiplication sort of thing. A number of quantum gates which I'm applying, and we here the entirely it is not like just like your classical system. Here we'll be comparing about what is the cost of each of your quantum gates. We have benchmarks where they talk about if it is an X gate, you have cost of that particular gate is 1. If I'm talking about CX gate, my cost of CX gate is 5. Controlled NOT gate, we have cost as 10. So by that, you add on, find the sum of the number of quantum gates you use, and you calculate your circuit cost. This is one. And another parameter which we look is the depth of your circuit. The number of parallel operations which you can do. That is one. And the other one is one is not what is the other one which I was talking about? Like the width, the number of qubits. So that can be another. The number of qubit is again depending upon the number of qubits you increase, your complexity of your circuit also gets increased. We don't directly go for calculating your matrix multiplication and say I'm having order of n squared. No.
I think, are you asking about the cost or are you just asking about the permutation?
So no, I think that partly addresses my question. So what I'm trying to understand is where is the parallelism coming from in quantum world? Is it that any matrix application on a vector, is it a unit cost or is it still function of number of bits? Like in classical world, if there is
Function
an
of
n bit.
number of qubits.
Okay. So if I have to do some uh, operation on n qubit system, let's say it's a valid matrix that I'm trying to apply on n qubit system, it will come out to be order n, is it? It will not that magically uh, the matrix will be applied in constant time.
Uh, I'm not able to get you. What do you talk about matrix, multiple matrix, applying matrix on constant time? What we do is we actually apply the matrix values of your kit zeros or kit ones, whatever you have, and take about the matrix of your X gate or whatever gate you're having, and you go for either calculating it on dot product or tensor products. So if I'm applying it on the same qubit, I'll be going for calculating using the dot product. If I'm applying it for multiple qubits, I'll go for tensor product.
Okay,
It is
makes
little bit of
sense.
math, and that it I have to like it depends upon I'm increasing my number of qubits, right? If it is for 2 to power 2, I'll actually go for finding out the tensor, taking from the first qubit to the second one, find the tensor product and get my values.
And Abhinav, I think one of the good books is Newman and Hilson and Chuang that go through the details of, and it's a classical book. I'm assuming Dr. Gandhi, you'll also recommend that. It goes through very detailed analysis of the questions that you are asking. Yeah.
Sounds good. Yeah, appreciate it. And I have one other quick question on your slide 20. There were three X's that you used, and you touched on that in your recap as well. So for one qubit, I want to get some more clarity. Why do we need three X's to represent it?
Why do we need?
Three X's to represent it. On your slide 20, you had a spherical 3D representation of a qubit. What is that helping us with?
Which one?
Slide 20. Yeah, this picture here. Why
Is
do
this
we
slide
have
20?
Yes, this 21, sorry. So why do we have three X's here? What is it helping us with?
Why do we have three axes? Okay,
Yes.
actually, we can compute on all of these bases. We have Z basis, we have X basis, and you're having Y basis. And as of when I'm talking about classical machines, we don't have these different bases here. I can transit from zeros and ones. I can move from to plus and minus state. I can compute on both X basis and Z basis here. I can move from one basis to another basis. Say, for
Eh,
example, if I'm in zero, yeah.
Got it. So we are trying to demonstrate uh, the fundamental, or maybe all bases can be presented here that are needed for one qubit system.
Yeah,
Okay,
yeah.
thank you. Yeah, that's all.
Thank you for your questions, Abhinav. Anyone else? I answered a few questions online. Meanwhile, one was about the book. So for Qiskit, I recommended IBM's online textbook, which is, I feel, is one of the best. But anything else, Dr. Gandhi, you would like to add there?
I have some of my slides for references. I can show you at that I can have. I think there is a mistake in the last page slide number 34. It should be NOR. Which one? Maybe let me recheck it. I'm not able to visualize which is slide number 34. Anyways.
Yeah, where you have your classical NOR. Yeah, the one, go back. When you had all the classical gates listed, classical NOT, and the last one is XOR, is a repetition of the first one.
Okay. Yeah. Thank you.
Thank you.
It is not over there. Yeah. It is classical. I had XORs twice. This
Yeah,
is not.
yeah.
And Harshavardhan, I have some of the textbooks I have in my next slide. I'll show you some of the references. Any other questions?
Nothing else. I think that's all we had. We'll probably have a follow-up session, and maybe next time, if time permits,
Mhm.
people can also do it and see if that is easier. But we can,
Okay.
yeah.
So this is for I'm not a part of IBM. I'm actually an IBM Qiskit advocate. We work on our own interest. If you're interested to become a Qiskit advocate, you can submit this table link. Once when they open it, you'll get an email notification. This is one. The other one is you have to make contributions to Qiskit code and community. So they look about last year or the previous year when they had applications open to Qiskit advocates, they had around 60 average of score of 60%. And once when you have your contributions, you can take up this exam. And if you clear, you will become an Qiskit advocate actually. So this is one. Learning resources, I would say you can join Qiskit Slack here. Slack has plenty amount of channels. Qiskit Cert exam channel is very, very interesting. Undergrads, general channel, quantum internships, textbook reading groups, and many, many things. And this is the link for creating an IBM ID, quantum experience ID. And this, benefits of becoming an Qiskit ID. You can become mentorships in various global summer schools, collaborations, advocate Fall Fest. You can organize Fall Fest. We organized at CIT for last 4 years. We have Advocate Cafe and so on. So these are some of my references which I have here. Say this is Qiskit textbook for the older version, but you have the latest Qiskit textbooks yet to come. This is for Slack. We also have localizations. This we did it earlier. And I would say if you're young students, do participate in various hackathons organized or challenges organized by IBM, Microsoft, Xanadu's, Google's, Rigidity's, NYUAD, and so on. And this is our YouTube video for CIT Quantum Hackathon, which we had. And some of the textbooks which I started with Nelson and Chang textbook in 2000, when I started in 2003. And later part, for my PhD, I worked on most of the parts of reversible logic, where I followed Alex papers and Rich Lesser and Willie papers. If you're interested in Qiskit, IBM Qiskit, James and Frank Harkin's IBM Qiskit Pocket Guide are really very nice books. Some more other good textbooks are, you can go for Thomas Wong textbook and Dancing with Qubits of Robert Swift. This will all help you actually. And these are some of our references which we have worked on quantum blockchain, some of book chapters which we worked. We have a paper on quantum drones, and this is which was part of my PhD, where we worked on various reversible logics. And this is as part of our projects which we worked recently. So all these are from QAM, where Qiskit Advocate Mentorship Program. Julian from IBM Switzerland, and Guncha, all are Qiskit advocates here. And this was part of Classic program which we worked last year. And Nati was our mentor there. And we worked really designing interactive introduction to quantum computing course using Classic. Thank you all. Thanks for joining here. And Taposh, thanks for invite. And I thank each one of you who participated, who joined my session too. Thank you once. You can reach me here using my ID.
Yeah. Thank you, everyone. Thank you, Dr. Gandhi. I appreciate it. I know it's late in the night for you. So thank you for taking the time.
Thank you, Taposh.
Bye.
Thank you. Bye.